Hello, everyone. My name is Haitao Meng, and I'm currently a first-year doctoral student at the Technical University of Munich. And it's really my honor to present our work here. And the topic of this paper is the GPU-accelerated deep stereo-LiDAR fusion for high precision, real-time high precision dense depth sensing, which was awarded as the best paper in date 2021. So firstly, I would like to talk about the motivation of this work. So we know that the capability of depth sensing is extremely important for robotics and autonomous driving cars. LiDAR and stereo vision are one of the most commonly used solutions to obtain the depth information for outdoor robotics. On the one hand, stereo vision could acquire dense depth information, but they are not reliable. And on the other hand, LiDAR could provide accurate and reliable depth estimation, but LiDAR could not provide the dense depth information. So actually, these two methods have complementary property for each other. So to achieve these properties, the one solution could be fuse the LiDAR data and the image data. So there are actually some the LiDAR and stereo fusion is not an easy task due to the following challenges. And the first challenge is generalization. So most DNA-based approaches perform extremely well on the testing set with similar sense to the training set. However, when moving to the unseen environment, the sensing accuracy will be significantly reduced. This is not acceptable in practical because the dataset cannot capture all the difficulties involved when deploying in the on the field. So as an example, the PSMNet, which is an excellent work for stereo matching, failed to predict depths when handling the custom images. And the second challenge is the prediction latency. So in general, we want to acquire the depth as fast as possible to predict potentially unsafety events. However, currently DNA-based methods tend to predict depths with deep and bounty neural network, which significantly increase the latency. So as shown in the video, LiDAR Stereo-LiDAR only achieve 1 frame depth estimation per second. It is obviously not acceptable for the real-time applications. The third challenge is the robustness. We expect the fusion algorithm is robust to various LiDAR inputs, such as misaligned LiDAR or very sparse LiDAR. Sometimes the system have to handle the situation that there is no LiDAR input. So basically, these are the challenges of the fusion task. To tackle the challenges, numerous efforts have been made, like this LiDAR Stereo-LiDAR, specific norm, probabilistic fusion, and HPED. However, these efforts have not completely solved above mentioned issues. The following table summarizes the shortcomings on the generalization, the robustness, the reliable, and the real-time performance. So it's clear that this method can not perfectly tackle this problem. So in our work, we mainly provide 3 contributions on the task of the stereo-LiDAR fusion. So the first one is that we proposed a framework to achieve the leading accuracy on unseen scenarios, showing the strong generalization. And the second contribution is that our framework is highly computation and memory efficient. The system can achieve high throughput with very less memory footprint. The third contribution is that our system is also robust to the LiDAR input. So our system shows little accuracy degradation when handling misaligned LiDAR data. So here is the overview of our framework, which consists of 3 fusion stages to fuse the LiDAR data and the image data. We did not construct the end-to-end architecture for the prediction. Instead, we use the BN as the preliminary matching likelihood generator, so that we could further integrate the LiDAR information in the following aggregation procedure and the refinement procedure to boost the performance on accuracy. We also found that this architecture works really well to prevent the network from over-specialized to the confound training set. Here, I would like to talk more about the third stage fusion. It's actually the extended work of the previous published paper on data conference. And we actually have already submitted this manuscript to the journal Field of Robotics. So next, I will introduce the fusion stage one by one. This page is for the first stage of fusion. And in this fusion scheme, we concatenate the LiDAR input and the image input and feed them to the BNN feature extractor to extract features jointly. We use the weighted Hamming distance metric to obtain the initial matching cost. And here we select the binary neural network instead of the fluid point convolution neural network, because we want to avoid the expensive fluid point and multiple operations. So this is the second stage of fusion. We proposed a cross-based LiDAR trust aggregation module to integrate the information of both LiDAR and the images. So basically, this module is to utilize the LiDAR information to guide the update of the matching cost for eligible pixels. But the eligible pixels here do not only include the pixels that corresponding to the LiDAR data itself, but also include the pixels that conform to the constraints in the nearby position. So there is an illustration in the bottom left here. The red arrow is the forward direction denotes in the forward direction denotes the eligible neighbor pixels to the center pixel. And to clearly describe this process, I prepared a page of slide to show the whole process of the cross-based LiDAR trust aggregation. So here we got the LiDAR and the image for the stereo-LiDAR fusion task for the depth estimation. Let me focus on this white car. So we have the input image on the left side, on the left side, and the LiDAR map on the right side. So according to our aggregation scheme, we first find a LiDAR pixel in the LiDAR map and its corresponding pixel in the input image. Here we find both of them and mark them right. Then we follow in one direction to check if the pixels are eligible by constraints like the maximum length and the density differences. Here I select a couple of pixels as the eligible pixels here. And then I will repeat the process in the other three directions to select more pixels, just like this one. And after we found these pixels, we will update the matching cost of these pixels. So here I will show a chart of the matching cost distribution. So in this chart, each column denotes the matching cost for each disparity candidate. In our aggregation scheme, we update the matching cost for all the pixels we selected based on the LiDAR information. So after we update the matching cost, like this one, this disparity candidate will be more likely to be chosen as the final prediction, because they have lower matching costs than others. And after we update this one, we have already finished the cross-based LiDAR trust aggregation. And this basically is the whole process of our aggregation scheme. So here is the third stage fusion. We build up a UNet-like network to refine the curve depth estimation, which generated in the second stage fusion. To reduce the computational complexity, we construct this network with really lightweight encoders and decoders. The most important thing for this part is that the third stage fusion actually is a component that can be optionally enabled or disabled for better trade-off balance between faster running time and the smoother depth estimation. So for the real-time performance of our system, we provide an integrated optimization scheme for the cross-based LiDAR trust aggregation to deploy it with almost neglectable actual overhead. So as illustrated in this figure, instead of implement the proposed aggregation as a standalone procedure, we integrate these two aggregations together by utilizing the census process of the SCM to update the matching cost beforehand. So eventually, two cost aggregation scheme included the cross-based LiDAR trust aggregation and SCM are integrated as a one implementation. So from the perspective of the hardware, so we only need one-time memory access. Therefore, we can save a lot of time on the data load and the data write. So for the experiments, we re-implemented all compared methods on NVIDIA Titan X Pascal GPU to guarantee the fairness of our evaluation. So for the dataset, we employ two challenging datasets, KT and ETH3D. We follow the existing work to build up the testing set for these two datasets. And in the next, I will show the performance on the proposed framework in the accuracy, the generalization, the robustness, and the real-time performance. So here is a qualitative result of the KT 2015 dataset. Comparing to the state-of-the-art method, the accuracy of our framework outperform MCN and the CCV norm by a large margin. Also, our work is slightly inferior to PSM-NITE and LiDAR Stereo-LiDAR. It's worth noting that our framework only takes 16.8 milliseconds with the 20.9 kilobytes model. So which is order of magnitude faster and 3 orders of magnitude smaller than its counterparts. So to evaluate the generalization, we test the method on the ETH3D dataset. It's really impressive that our work achieved the best accuracy among all accuracy metrics with only less than 16 milliseconds of computing. So in contrast, the PSM-NITE, CCV norm, and LiDAR Stereo-LiDAR experienced several accuracy drop on this new unseen dataset. So it means that our work is more generalized to the real-world applications. So to evaluate the robustness of the method, we conduct experiments that employ the different lines of misaligned LiDAR input. As shown in the figure, our work could reconstruct depths with little accuracy degradation, even there is no LiDAR input. So, I mean, it's really show a strong robustness. So here is a video demo in comparison with other two state-of-the-art stereo-LiDAR fusion method. So we illustrate the image input and the sparse LiDAR input in the first row, and the prediction of two state-of-the-art function method on the second row. And the third row is the depth estimation of our framework. So basically, we achieve the comparable depth estimation results with two state-of-the-art methods. But our system has a clear lead on the in the training speed. So specifically, two-stage disparity prediction can reach at 59 LPS, and three-stage disparity prediction can reach at 21 LPS. So in comparison to counterparts only achieve like 1 FPS. So our system is really practical to be deployed, to be deployed in the real-time applications. So to conclude this talk, we present a novel stereo-LiDAR fusion framework to generate accurate dense depth map in real-time and robust manner. We propose a three-stage stereo-LiDAR fusion scheme that is practical to the real-world applications. We achieve leading accuracy when compared to the state-of-the-art methods and the unseen scenarios. So this is the end of my talk. Thank you for your time. Thank you.
Okay, thank you very much. The LiDAR research is very important for the new vehicle. Yeah. So, but now we have two questions on the chat box. Can you look at the chat box? Can you see the chat box questions?
Okay.
Yeah,
so,
the first question is can you see in the experiment that you evaluate methods with Titan and yeah.
Okay, I see one. So which is the powerful GPU? Okay, So actually, this is a really interesting question. So indeed, the GPU we use is a powerful desktop device because it's a Titan Pascal GPU. But actually, our method is also capable on the embedded device. So we actually have tested our method on the embedded device, and we could achieve around 15 FPS depth estimation. We test on the NVIDIA Jetson the VIA device. I think with more dedicated optimization on the VIA device, like by taking advantage of the new Turing architecture and the tensor core, I think around 20 FPS prediction could be expected. For this question, I also want to mention about the computing capacity of the autonomous driving, because they are really similar and really in the application scenarios. So nowadays the computing capacity of autonomous driving is also powerful. So as far as I know, the new autonomous driving car equipped with four NVIDIA Drive Orin chips, which equivalent to NVIDIA RTX 3080. So it's really a powerful GPU. And I mean, RTX 3080 is really enough for almost any algorithms. So for this question, the directly answer is yes. Our method is still practical, no matter on the embedded device or for the autonomous driving cars. So this is the answer for this question. And I got another one.
The second one is about whether your solution can be used on low level GPU.
I think it's really a similar question, and I already answered in the first one.
True. Yes.
So there's also one. What is a precise definition of the robust in your system? So actually, this is like I can show my slides. So the definition of robust, I mean, it's like the robust is for the capability that the model can tackle the problem of the input data. So we know that it will happen if the LiDAR is mounted and also it's not calibrated very precisely with the camera. So there may be some disaligned LiDAR input data with the images. So if we too much depend on the precise data from the image and the LiDAR, then if we applied the algorithm to the applications in the real world, they maybe get some wrong, just like this one. We got the experiments on this thing. So this one. So in this experiments, we actually use varying level of misaligned input LiDAR. So actually the LiDAR is misaligned with the images. It means that the LiDAR will provide the wrong information to the model. And at this time, the model should also tackle this problem so that it can also provide a high precise depth estimation. So I mean, in my opinion, the robustness of this of the model is the ability to tackle the problem of the noisy inputs of the LiDAR data.